So what if I told you that the entire digital foundation of our modern world, your smartphone, the cloud, all the crazy AI breakthroughs happening right now, depends on a machine that costs over $350 million.
And that's if you can even get on the list to buy one.
Right. And that it works by, and I'm not making this up, literally exploding tiny droplets of liquid tin 50,000 times a second.
With a massive laser.
Welcome to the deep dive. Today, we're going way, way down the rabbit hole on what might be the most complex, most expensive, and frankly, most important manufacturing tool ever invented. Extreme Ultraviolet Lithography, or EV.
And that is the perfect way to frame it. Our whole mission today is to unpack the pretty dense research literature on this. Why would anyone spend 30 years and more than $30 billion on this one technology?
Why would they?
Because EUV is really the only way we can keep shrinking chips. It's the only practical path to get below a critical dimension of about 20 nanometers, which you absolutely have to do for the kinds of sub-5 nanometer chips in your phone right now.
So we're going to dissect this thing from the ground up. We're talking about the unique physics, the explosive source that creates the light, the absolutely mind-bending mirrors that guide it.
And maybe the most important part, the fundamental limit. The fight against pure randomness, what the industry calls stochastic defects.
It's a multi-billion-dollar fight against chaos. I love it.
So let's start with the light itself. That's the foundation for everything. EUV light, what is it? Well, it operates at a wavelength of just 13.5 nanometers.
Which is incredibly small.
It's a huge jump. It's about 14 times shorter than the old workhorse, which was deep ultraviolet, or DUV, light at 193 nanometers.
Okay, I have to ask. That number, 13.5 nanometers, it sounds so specific, so random. Why that exact wavelength?
It's actually a fascinating engineering compromise that was made decades ago. You know, the basic physics, the Rayleigh criterion, says if you shorten the wavelength, you can print smaller things.
Simple enough.
But the problem with EUV light is that everything absorbs it. Air, glass, you name it. So you can't use traditional lenses like in a camera. You have to use mirrors.
Like in a giant telescope.
Exactly.
Yeah.
And it just so happens that the best mirrors we could figure out how to build, these incredibly complex stacks of molybdenum and silicon, or MoSI, they have their peak reflectivity at, you guessed it, 13.5 nanometers.
So we didn't pick the light. The mirror picked the light for us. We had to use the one wavelength that the only mirror we could build would actually reflect.
That's it. It was a practical choice. But then, of course, you have to actually make that light. And that part is, well, it's straight out of a Marvel movie.
You called it the explosive heart, which sounds about right. We're in a total vacuum, so you can't just flip on a light bulb.
No. You have to use something called a laser-produced plasma source, or LPP. This is where ASML and gigaphoton are the big players. And here's the wow factor. You take a massive, high-power QOVUO laser, and you focus it onto tiny droplets of liquid tin.
Liquid tin, not a solid, not a gas. A droplet.
A tiny one, about 30 micrometers in diameter. Think a third the width of a human hair. And you fire these droplets into the chamber at 50,000 per second.
50,000 times a second. That's just, I can't even picture that.
And each time that laser blast heats the tin to 20 to 50 electron volts, it instantly vaporizes into a super hot plasma. And that plasma is what flashes and emits the 13.5 nanometer light we need. It's controlled atomic level violence.
Okay, so when you're running a multi-billion-dollar fab, what's the one number you care about here? The one metric that decides if this insane machine is even profitable?
It's all about conversion efficiency, CE. How much of that colossal laser energy actually turns into useful EUV light?
And I'm guessing it's not very efficient.
Early on, it was terrible. Like 1 to 2%. Today's systems are much better, maybe 4 to 6%. Gigaphoton recently published work showing they hit 4.7% just by tweaking the timing of a little pre-pulse laser that hits the droplet an instant before the main blast.
But even at 6%, that means 94% of your energy is just wasted as heat before the light even gets out of the chamber.
Right.
And I have to imagine exploding metal 50,000 times a second creates a bit of a mess. Debris has to be a nightmare.
Oh, it's the biggest technical headache of the entire system. You
Yeah.
hit on it. The plasma creates these high-velocity tin ions. We're talking up to 10 kilo electron volts, plus molten tin splatter, tin vapor.
And it's all flying right at the first mirror, the collector mirror that's trying to catch the light.
The one sitting millimeters away from the explosion.
Yeah.
If that tin coats the mirror, its reflectivity just plummets. It's a maintenance disaster.
So what's the defense system? You can't just send someone in with a cloth to wipe down a $70 million mirror.
No, it's much cleverer. It's a two-pronged attack. First, they fill the chamber with a little bit of hydrogen gas.
Okay.
The hydrogen does two things. It physically slows down the tin ions just by bumping into them. And second, the really neat part, it chemically reacts with any solid tin that does stick to the mirror and turns it into a gas called STANAN.
So it turns the solid metal gunk into a gas you can just pump away.
Exactly. You just pump it right out. It's an elegant solution. But it's not perfect. The hydrogen itself can cause damage over time.
Then it must be something else.
The newer innovation is using magnetic fields. Basically, a magnetic trap that grabs those highest energy ions and steers them away so they never even get a chance to hit the mirror.
Okay, so we've managed to create a tiny flash of light and keep the first mirror clean. Now we have to get that light all the way to the silicon wafer.
And this is where the physics gets brutal. We're in a hall of mirrors, an optical maze, and a complete EUV system uses somewhere between 8 and 10 of these reflective mirrors to shape the beam and shrink the image.
But you said earlier, even the best mirror only reflects about 75% of the light.
Around 70 to 75%, yeah, which means it absorbs 30%.
And when you multiply that loss across 10 mirrors, the numbers must be devastating.
They are. The shocking result is that only about 1 to 2% of the EUV light that was generated by that tin plasma, only 1 or 2% actually makes it to the wafer.
1%. You lose 99% of the light along the way.
Which is why the source has to be so ridiculously, unbelievably bright to begin with, just to get enough photons to the finish line to expose the wafer.
That inefficiency is staggering. And that brings us to the scanners themselves, the machines that do the actual printing. ASML is basically the only game in town here.
That's right. For years, the workhorses have been the low-NA systems, like their NXE 3400C. These are the machines that built the 7-nanometer and 5-nanometer chips that are probably in the device you're listening on right now.
And those cost, what, around $120 million?
In that ballpark, yes. And they can process about 136 wafers an hour. Very productive.
But now we're moving to the next generation, the next frontier, the high-NA systems.
This is the TwinScan EXE 5000. And this is where the price tag and the complexity just explode. It increases what's called the numerical aperture, or NA, from 0.33 to 0.55.
In simple terms, what does a bigger NA get you?
Better resolution. Plain and simple. It lets you print features down to 8 nanometers. That's a huge leap, a 1.7x improvement. And it's what you need for the 3-nanometer and 2-nanometer nodes.
With a price tag to match, we're talking $350 to $380 million for one machine.
We are. And the cost comes from the optics. We're talking about 6 massive custom mirrors from Zeiss. Each one can be up to 1 meter in diameter. They cost over $70 million apiece.
And the precision is just off the charts.
It's almost hard to comprehend. They are polished to a surface roughness of just 20 picometers.
Okay, 20 picometers. Help us understand that scale. A picometer is a trillionth of a meter.
Here's the analogy I use. If you scaled one of those mirrors up to the size of North America, a 20 picometer bump would be the size of a single grain of sand.
A single grain of sand on a continent-sized mirror. That's the limit of what humanity is capable of polishing.
It really is.
But here's the big twist in all the research. After all that effort, all that money spent on perfect mirrors and explosive light sources, the ultimate limit isn't the machine anymore. It's the physics.
This is the real story now. And it all comes down to the energy of the photons. The old DUV light had about 6.4 electron volts of energy. That's actually pretty low.
But EUV photons are like cannonballs in comparison.
Exactly. They have 92 electron volts. That's so much energy, it causes what we call indiscriminate ionization. It just blasts electrons off of everything in the photoresist, the light-sensitive chemical on the wafer.
And those flying electrons are the real problem.
They are the fundamental bottleneck. When a 92 EV photon hits, it creates a cascade of what we call secondary electrons. And these little electrons travel, on average, about 10 nanometers through the resist before they stop.
Wait, so if you're trying to draw an 8-nanometer line, you have this unavoidable blur of electrons spreading out 10 nanometers.
You've got it. It's a fundamental chemical blur. The effect of the light gets averaged out over a space that's bigger than the feature you're trying to print. It's like trying to spray paint a pinstripe with a fire hose.
And that leads to this brutal trade-off everyone talks about. RLS resolution, line with roughness, and sensitivity.
Precisely. You can't win. If you make the resist more sensitive to speed things up, the lines get rough and jagged. If you try to make the lines perfectly smooth, you lose resolution. It all comes down to randomness. Photon shot noise.
We're literally dealing with the quantum randomness of a few hundred photons landing in one spot.
Which leads to stochastic defects. Random failures. A bridge forms where it shouldn't or a line breaks where it shouldn't. You're fighting chaos at the atomic scale.
So how do we fight back?
With new materials. There's a team, Tagawa and his group at Osaka University, who pioneered something called photosensitized chemically amplified resists, trying to get more control over the chemical reactions.
And I saw research on adding heavy metals into the resist itself, things like hafnium or zinc.
Yes, that's a big push. The idea is that these heavier atoms are better at absorbing the EUV photons. They can increase absorption efficiency by, say, 17%. More absorption means more signal, less noise. It's a direct chemical counterattack against that physical blur.
And it's not just chemicals, but processes too, right? Lam Research just announced something called ether dry photoresist.
Right, which they claim significantly improves sensitivity. So the whole industry is attacking this stochastic problem from every possible angle.
Okay, let's talk about another huge bottleneck and cost driver, the photomask. This isn't just a stencil, it's another one of these multi-million-dollar reflective mirrors.
It is. A blank mask costs anywhere from $500,000 to $2 million. It's another one of those MOSI mirrors, but with an absorber layer of tantalum nitride on top to create the pattern.
And the light hits it at an angle, which I read causes even more problems.
It does. It hits at a 6-degree angle, which is necessary for the optical design. But that slant creates weird 3D effects, like shadows from the absorber pattern that distort the final image on the wafer.
So you need incredibly smart software to predict and correct for those distortions before you even make the mask.
Exactly. You need massive computational lithography, something called source mask optimization, or SMO, just to get a clean print.
And with 3-nanometer chips, you have this zero-defect imperative. One tiny flaw on that $2 million mask can kill millions of dollars in chips. But checking the mask is a huge problem.
It's a massive bottleneck. You have to inspect it with EUV light itself. That's called actinic inspection. But the tools are painfully slow. ASML's inspection machine can only check a few hundred fields per hour. It's a major choke point in the whole supply chain.
So we have an outrageously expensive, physically limited machine that needs perfect, multi-million-dollar parts. Now let's connect this all back to the energy. All that inefficiency we talked about, the 99% light loss. What's the power bill for this thing?
The resource demands are pretty staggering. A single EUV tool consumes about 1.3 megawatts of power.
Which is how much more than the old DUV system?
It's the 10-fold increase. A DUV scanner was around 0.13 megawatts, so using 10 times the power to print one layer.
That's a shocking jump. How does that scale up across the whole industry?
Well, the projections in the literature are sobering. By 2030, all the EUV-equipped fabs in the world are projected to consume 54,000 gigawatts of power annually.
54,000 gigawatts. Put that number in context for us.
It's more than the entire national power consumption of Singapore.
Wow.
And that's not even counting the water. A single one of these large fabs needs up to 38 million liters of ultra-pure water every day. That's the same amount of water that 300,000 people would consume.
So the price of Moore's Law is not just financial, it's environmental.
It imposes immense resource demands, absolutely.
Okay, so with all that complexity, let's quickly touch on the industry race. Because just buying the machine doesn't guarantee success.
Not at all. We've seen 3 very different strategies. Samsung went in early and aggressive back in 2018, 2019, but they really struggled with yields for a long time.
Then you have TSMC.
TSMC played much more conservatively. They waited, used EUV on just a few layers at first, and only scaled up aggressively once they had mastered it. They are the undisputed yield kings today.
And that leaves Intel, who came to the party late.
Right. Intel is the late adopter, but now they're trying to leapfrog everyone with massive investment. They're installing the very first public high-NA EUV system in 2024, betting that they can use this next-gen tool to reset the competition. It's a huge gamble.
A huge strategic gamble on a $380 million machine. So let's wrap this up. What does all this mean for you, our listener? We've got 3 key takeaways. First, the fundamental limit has totally changed. The biggest fight in chipmaking isn't just optics anymore, it is basic physics. It's the stochastic defects, that inescapable 10-nanometer blur and photon shot noise. We are literally fighting against randomness.
Second is the sheer scale and cost. A high-NA tool at over $350 million is the most expensive manufacturing machine ever built. But paradoxically, it actually helps reduce the cost per transistor because it lets you get rid of all the complex, yield-killing, multi-patterning steps you'd have to do otherwise.
And third, and this is not an exaggeration, the entire semiconductor industry has bet the future of Moore's Law on high-NA EUV. They're counting on it for the 2-nanometer node and beyond, to the next-gen Hyper-NA systems that could cost over $700 million.
And that combination of extreme complexity, the capital required, and the huge environmental footprint, it creates this massive execution risk. It's why advanced chip making is now limited to just a tiny handful of companies in the world. Only the biggest of the big can even afford to play this game.
Thank you so much for joining us for this deep dive into the $30 billion key to our future. And we'll leave you with a final thought to chew on. If keeping Moore's Law alive means building machines that will soon consume more power than an entire country, what does the sustainability of our technological future actually look like when we finally run out of electrons to control? We'll be back next time with another deep dive. Make sure you subscribe to the channel so you don't miss it.